Today we're going to do 2.5 exponential function, context, and data modeling. An exponential functions model growth patterns where successive output values over equal length input value intervals are proportional. As a reminder, the general form of an exponential function is f of x is equals to a times b to the power of x, where a is the initial value and b is the base, a positive number other than 1. The base represents the constant proportion by which the output value is multiplied at its step. So these are the conditions. When b is greater than 1, the function demonstrates exponential growth, meaning that the output values increase at an increasing rate. When b is between 0 and 1, that means b is less than 1, the function demonstrates exponential decay, increasing that the output values decrease at a constant decreasing rate. So when the input values are whole number, exponential functions model situations repeated multiplication of a constant to an initial value. So once a model has been created, we need to apply it to the context and verify that it works the way we had intended. So if the results from our model do not appear to be accurate, we can revisit our assumptions and repeat the modeling cycle. So exponential function can be difficult to identify from a graph or a table when the amount of change is small relative to the size of the numbers. So let's look at it in this example. Consider the data from the U.S. Census for its decade in the 20th century. So you have from 1900 to 2000 year, okay? So the population in 1900 is 76.2 millions. In 1910, we have 92.2. Until 2000, we have 308.7 millions. The function p of t is equals to 76.2 times 1.136 to the power of t over 10 has been created from the table to find the population t years after 1900. The question is, first question, find the 10-year growth, the growth factor for its decade, and compare it to the growth factor of the model. Now remember that the growth factor can be found by dividing its decade population by the previous population. So for example, we're gonna use from 1900. Okay, so from 1900 to 1910. Because this is a 10-year growth. So we're gonna use this to find the growth factor between those two set of years. So what is the population of 1910? We have 92.2. And then we're going to divide it with the population in 1900, which is 76.2. So we come up with a 1.210. Okay? So I could start writing the growth factor between 1900 to 1910 by writing the growth factor here as 1.210. Now, to complete that column for growth factor, you can do the same thing by doing that from 1920 to 1910, okay? Or 1910 to 1920. So if we do that, 1910 to 1920, so we have 106, get the ratio, divided by 92.2. Then you come up with 1.150. And that will be the growth factor here, 1.150. By doing the same thing, we get the growth factor between 1930 to 1920. So 122.8 divided by 106, we come up with 1.158. The 1940, between 1930 to 1940, so we divide 132 by 122.8, we come up with 1.077. Then do the same thing from 1940 to 1950. You divide 150.7 by 132.2. We come up with 1.190. Then between 1950 to 1960, we have 179.3 divided by 150.7. We have 1.140. Then from 1960 to 1970, we have 203.3 divided by 179.3. We come up with 1.134. Then from 1970 to 1980, so we do 226.5 divided by 203.3. We come up with 1.114. Between 1980 to 1990, we divide 248.7 divided by 226.5. We come up with 1.098. And the last is from 1990 to 2000, we have 308.7 divided by 248.7. We come up with 1.241. So the growth factor of the model, from the model itself, we have a 1.136. This is the growth factor of the model, which is larger than the growth rates from 1930. So what's the growth rates from 1930 to 1940? We have a 1.158 and 1.077. So 1.077 is less than 1.136. And 1960 to 1990. So this is 134, 1.114, 0.098. That means the 1.136 is greater than this growth factor in the years that are mentioned. But it's less than the growth rates from 1900 to 1930 because we have 1.210 and 1.150. So the 1.136 is less than this in these years. And also from 1940 and 1950, we have 1.190, and also 1990 to 2000 we have 1.241. So these are the values that are greater than the growth factor of the model, which is 1.136. So the growth factor in the model appears to be an average growth rates across the century. So the decade from 1930 to 940 had a very small growth right here. A very small growth rate, which likely due to a Great Depression, but other historical events might have influenced population growth. Okay, let's go to letter B. Determine the decades in which the model is at least accurate. So we will use the function that is the given function, which is f of x equals 76.2 times 1.136 to the power of t over 10. To complete a table to estimate the population, then we can find the difference between the estimated population and the given population. All right. So let's say in 1900, it's 76.2. So this still, if we have to look at the population mentioned, so this is still the estimated population at this time. So we're going to start with 76.2. All right. So by doing that, okay, let's go back to here. From the function itself, 76.2 times 1.136. Okay, let me get my calculator. So 76.2 times 1.136. We have 86.56. (1.36) because that time here t is 10, so 10 over 10, that's to the first power. Okay, so that means it's equals to 86. We just rounded off 86.56 or approximately 86.6. And that is how we got the next estimated population. So this will be 86.6. Now, do the same thing. You're going to do 86.6 times 1.136. We come up with 98.3. So as I've said, for this is the first estimated, then from 86.6, you multiply with 1.1. Okay, I'm not going to use the x. Just have the parentheses. 1.136. Still between 1910 to 1920. It's 10 years, so 10 over 10. When we have 10 over 10, that's still 10 to the first power. So the result to that, we have 98.3. Okay, 98.3. Right? Do the same thing, the same process. 98.3 times 1.136, you come up with 111.1. Then 111.1 times 1.136, you come up with 126.9. 126.9 times 1.136, you come up with 144.2. 144.2 times 1.136, you have 163.8. Then 163.8 times 1.136, you have 183.0. Then 183 times 1.136, you have 211.3. 211.3 times 1.136, you have 240.1. Then 240.1 times 1.136, you come up with 272.7. Okay. So the model underestimates the population in every decade except in 1900. Okay. So the least accurate decade is 10,000. Is in the year of 2000, when the population estimate is off by 36 million. That's quite a big difference. So it's quite off. So a graph can be useful to this. When we use our calculator, we can visualize the better model, and we can visualize both the data and the function. So by getting the difference, because we just want to know what's the difference between the population and the estimated value in its year. Like, of course, we start with a zero difference here. So how much is 86.6? What's the difference when you have 86.6 and then you subtract with 76.2? Oh, hold on. 98 minus 86.6. Um, 92.2, 86.6, we come up with the difference of 5.6. All right. Then we have 106. Let's see what's the difference from to 98.3. We have 7.7. This is between the population and the estimated population. So when we have 122.8, get the difference from the estimated 111.1. We have 11.7 difference. So 126.9 from 132.2. We have 5.3. So 144.2 from 150.7. We have a negative 6.5. Then 163.8 from 179.3. We have a negative 15.5. Then 183 from 203. We have let's see if I miss out something here. 0, 5.6, 7.7, 5.3, 6.5, 15.5, 17.3. All right. Then 211.3 from 226.5. We have negative 15.5. And 240.1 from 248.7, we have a negative 8.6. And 272.7 from 308, we have a negative 36. So it's off. As we said, from the year 2000, the difference is quite, the decrease is quite that off. All right. Now, as I've said, you can see visually all these values when we use a calculator. All right. When what if we add a constant? In some cases, a data set may not immediately reveal an exponential growth pattern, even though the relationship between the independent and dependent variables is actually exponential. So one reason for this is the initial value of the dependent variable may not be 0. So in such cases, a constant may need to be added to the dependent variable values of the data set to reveal a proportional growth patterns. So just like, for example, let's say we have a data set that represents the population of a certain city over time. So the data set may not show an exponential growth pattern because the population has always been greater than 0. So if we want to analyze the population growth rates, we may need to consider a population growth as a proportion of initial population. Okay? To do this, we can add a constant, say, k to that. Okay? We say add a constant k. All right? To the population values. So the new dependent variable we may have y would be y to the first would be y plus k. How we can analyze the growth rate of y to the first power over time, which will be all proportional. So another example could be the start of an investment right here, or exponential growth of $1 for 30 years. So the investment that starts at a certain value and the growth rate not immediately visible until we add a constant to the value of the investment. So we can see here with this graph and how the exponential growth happens after 30 years. So it's very visible to that. That's why we add a certain value, a constant value, which is k. So a graph with a different percentages or percentage of growth rates from least in most curve demonstrate growth. Okay, let's do this. As I've said, we'll be getting a certain proportional value and add it to get you know, the function. Okay, below is a table of values for exponential function in the form of f of x is equals to a times b to the power of x plus k. This is the k I'm talking about. Write the equation to represent its table. Okay. We have an x value and a y value, a 0, 1, 2, 3, 4, and we can see that if we graph this using a calculator, we can see how the graph looks like. All right, let's say we know that this is exponential actually by looking at the y value. So let's get the difference between 7 and 16. So 16 minus 7, that's equals to 9. Then 34 and 16, we have 18. 70 and 34, we have 36. 142 and 70, we have 72. So by looking at this, we still cannot get the ratio factor, to get the b. So we need to think about a certain number that gives us in order to connect it to the successive data. Okay? By multiplying that proportion value. Okay? So in other words, we know that what number should we multiply to get 18, to multiply to 9 to get 18. We could see that if we multiply it by 2, we could have 18. Same thing with 18, multiply by 2 to get 36. And 36 multiply by 2 to get 72. So in other words, to set or to get us the succeeding term, we would able to get the proportional. We call it the proportional value, which is 2. And we call this as our b. All right, this is the proportional value. And that would be the v. Okay, in other words, that's the factor when we use or when we get the v. Remember, in the exponential form. to that. All right. Now let's have a pair, first pair, to make in order for us to write down the uh, exponential function. F of x equals a b to x to the power, to the power of x plus k. So we can use the x and the y value of the first column here, where the y would be 7 and a, we don't know a, but we know the b, which is 2, and x to the power of x, which is 0. Then we add the k. All right. 7 equals a 2, any number raised to a 0 power that's equals to 1 plus k. So we have 7 equals a plus k. All right. We pause for a while because it seems that we have two unknown values here, which is a and k. So we'll get another pair of coordinates. Second pair, so when the f of x is 16, a times b, which is 2 to the power of 1, since our x now is 1, plus k. So we have 16. 2 to the first power is 2 times a, that is 2a, plus k. All right. Now, how can we have two equations with a and k. So in other words, let's simplify the first one here to get the k value. So we transpose, that would be 7 minus a equals k. And then substitute it here to this equation, 16 equals 2a plus 7 minus a, substituting the value of k. Okay? So what unknown variable we have now is a. All right, so we can solve a from here. So transpose 16 minus 7 would be 2a minus a is equals to a. So a would become 16 minus 7, that's equals to 9. So we have now the value of a. So from here, to find the value of k, we substitute the value of a, which is 9, equals to k. So k is equals to -2. So we have now the value of a, the value of k. So in other words, we can write now our function. So our equation. So our equation here would be f of x equals a. Our a is 9 times b, which is 2, to the power of x, plus our k is -2, that means -2. So this will be the equation. For this table, this will be the equation. All right. Let's have another one. You have the x value, 0, 1, 2, 3, 4, and the y value. So as I've said, get the difference first. From 4 and 13, the difference is 9. 49 and 13, the difference is 36. 193 and 49, the difference is 144. 769 and 193, the difference is 576. All right. We cannot see a common factor here, or the how do you call this? In order for us the growth factor, we know this is exponential, but we can we can tell from 9 to 36, we can get a connection. How will we go to from 9 to 36? That means if we try to multiply by 4, we come up with 36. In 36 by 4, we come up with 144. And 144 times 4, we come up with 576. So in other words, our V value is equals to 4. All right. So do the same thing. Use the first coordinate as your trial to get the A and the K. So, sorry for that. We'll start with 4. A times the B is 4 to the 0 power plus K. So 4 is equals to A times 1 plus K. So 4 is equals to A plus K. Let's have another pair of coordinates. So we'll have 13 equals A times 4 to the first power plus K. So 13 is 4 to the first power is 4 times A. That's 4A plus K. So we have this equation and this. We have two unknown values, which is the A and the K. So in other words, we can simplify the first equation here by isolating the K. That would be 4 minus A equals K. All right. So we substitute that value of K in this equation. So this will be 14A plus 4 minus A, substituting the value of K. So 13 transpose 4 to the left, 4A minus A, that is 3A. 13 minus 4, that is equals to 9, divided by 3. Okay, I'll have it here. 9 equals 3A, because 13 minus 4, that's 9, equals 3A. That means I doubled it. That means A is equals to 9 over 3. So A is equals to 3. So we have the value of A. We can solve now the value of K. All right. So that would be 4 minus 3. So K is equals to 1. So we can now write our function f of x equals A is 3, B is 4 to the power of x plus 1, which is our value of K. So this is the equation. All right. Let's have a quick review of what we have learned in this lesson and connected to the other lesson. This is, let's say, a very easy, quick review. And let's say if we have remembered something from what we have learned. All right. So let's say if b is greater than 1, what is the end behavior for an exponential function f of x equals b to the power of x as x approaches infinity? As x approaches infinity. That means positive infinity. A, well, it approaches 0. B increases without bound. C decreases without bound, and D remains at constant at B. The answer here would be increases without bound. Why? Remember that for every base greater than 1, remember, for every base greater than 1, as x approaches infinity, the f of x value, b to the power of x, it grows, the value grows exponentially if it's greater than 1. Larger without bound or without upper limit. All right. Can have that. That means without bound. What is the base of an exponential function represented by y equals 3 to the power of x? Is it 3 times e, letter b 2 times y, letter c 1 times x, and letter d 3? Right? The answer here is D. To an exponential function, y equals 3 to the power of x, the number being raised to a power, which is x, is what we call the base. This one, this is the base. If you remember that in the exponents, when we did the exponential function, is called the base, and how it is, the base here is equals to 3. All right. Number 5. What is the product of the expression 4 to the power of x times 4 to the third power? This is 4 to the y power. All right. Is it 8 to the power of x plus y, b to 4 to the power of x plus y, c is 16 to the power of xy, d is 4 to the power of xy. Okay? When multiplying two expressions with the same base, remember the power property. Okay? You add the exponent. So that means if we have the base, our base is 4, and our exponent is x and y, we're gonna add the exponent x plus y and make the base as 1. Okay? That's a power property rule. So that means our answer here is letter B. Let's have number 6. Which expressions represent a division of two exponential terms? A to the power of m. It's division, that means it divides by a to the power of n. Remember that when dividing two expressions with the same base, so our base here is 8, so they are the same, you subtract the exponent. Okay, that means have the base as 1 and subtract the exponent. The numerator exponent is m minus the denominator exponent is n. So which of this gives us the right answer? The letter D. Okay. For number 7, what is the simplified result of 2 to the third power raised to the second power? This is coming from a power to a power property. Okay. So we multiply. Remember, when you raise a power to another power, you multiply the exponent. That means this is 3. This is 2. 3 times 2, it's 6. So if you multiply 2 6 times, 2 times 2 times 2 6 times, you will get 64, which is letter C. All right. Before closing up, let's have an additional reminder. I'm not doing this in 2.5 because it needs like a technology using a calculator, and I will be doing that in some other videos. So exponential function models can be constructed for, with this data set with the use of technology, especially when we do what are this exponential regression. All right, when we do that, we will use our calculator. So I will be doing a certain video on this. We're all using calculator. And exponential regression is a method used to fit an exponential function with a set of datas. So this method can be used to find the best fit exponential function that models the data. But there are some other ways to perform exponential function, and one is, finding the correlation coefficient. This is one also. We'll be doing that. This correlation coefficient. You have also correlation coefficient in statistics. All right. And also about residuals. All of this we are using technology, like using the calculator. And there is another one that I would like to emphasize, which this letter symbolizes E. This is, the E here, it doesn't look good. This is the natural base. And we call it the natural base E, which is approximately like 2. E value is approximately 2.718, and so on and so forth. It's like the value of pi, wherein until now it still keep on going, and the digits here are not repeated. So you have 2.718, and actually 2.71828182824, and so on and so forth. You cannot see a repetition like 2.7777. No, you cannot see that. The same thing as you have the value of pi, 3.1416, and so on. This is denoted by one of the reasons why E is used is as the base in exponential functions. Maybe we could see an f of x like e to the power of x, and we model that for continuous growth. Okay, when the growth is continuous. All right, so one of the reason why we use e as the base in exponential function, because it has a special relationship with the concept of continuous growth. So for example, this function f of x is equals to e to the power of x, which model that growth like investment that earns a constant interest rate. Imagine investment. So when we have problems about investments, hold on, what's going on? That earns a constant interest. So imagine constant interest. So the interest will be either go down or go up, but it is constant rate. And what would that rate be? Of 100% constant rate. So the function f of x would be e to the power of negative x that models. Okay, if you have, we can see something. Oh, sorry. Oh, what's going on? E to the power of negative x. So these models are continuous decay. Okay, of a substance that decays at a constant rate. So if you have e to the power of x, that is continuous growth. All right. So we'll be doing this later on. Why e is used as the base of exponential function. That is the base of the natural logarithm. Okay, natural logarithm as well. And that is denoted by ln. Okay, the natural logarithm is the inverse function of the exponential function with a base e. We'll do more on this in the coming videos. I'm just reminding you at this point, by using the e and using the calculator for technology, for exponential regression, correlation coefficient, and finding the residuals. All right, we'll be doing that in our incoming videos. So let me say this: if I can do it, so can you. Don't forget to hit the like button and subscribe button. See you in my next video.